Hey guys, welcome back to another lecture video for Chem 115. In the previous lecture video, we discussed how changes in pressure or volume generally affected the position of the equilibrium for any given chemical reaction. And so now that we discussed the theory behind the changes in pressure or volume with respect to Le Chatelier's principle, we're going to go ahead and apply what we learned to a few class examples. So the first example I want to go over is an equilibrium between sulfur trioxide producing sulfur dioxide and oxygen gas. So I want you guys to imagine that this equilibrium is inside some type of container such as a balloon. And so how will the equilibrium shift when you increase the pressure of the balloon or decrease the volume of the balloon, which is going to represent our container? And so if you recall from the previous lecture video, when you increase the pressure or decrease the volume, the equilibrium will shift in favor of the side with the least number of particles. And so to predict how the equilibrium will shift just by simply looking at this balanced chemical equation, we're going to count the number of particles on the reactant side and the product side. And so here on the reactant side we have 2 particles, on the product side we have 3 particles. And so according to Le Chatelier's principle, the equilibrium will favor the side with the least number of particles to essentially alleviate the added pressure on the system. And so I'm going to go ahead and draw a single-headed arrow pointing to the side of the reactants. And so overall, the equilibrium will shift to the left. And once again, shifting the equilibrium to the left will allow the particles that will consume the side that has more particles to the side that has less particles, thereby alleviating the added pressure that was placed on the system. All right, and so let's go ahead and take a look at another scenario using the same chemical equation. And so how will the equilibrium will shift when there is a decrease in pressure or an increase in volume of the container? And so imagine that you guys have a balloon and a chemical equilibrium has been reached when you kind of squish the balloon. And so now you're going to increase the volume of the balloon and decrease the pressure of the balloon by letting the balloon go. And so when you let the balloon go, it's going to go back to its original shape, thereby increasing the volume. And when you increase the volume, you decrease the pressure. And so according to Le Chatelier's principle, the equilibrium will shift to the side that has a greater number of particles. And so the reason why it shifts to the side that has a greater number of particles is to kind of compensate for that pressure that was lost. And so here in this case, since the product side has 3 particles versus the reactant side, which has 2 particles, there's going to be an overall shift in equilibrium to the right, in favor of the production of products. And in this scenario, since products has more particles, the conversion of reactants to products will allow the particles to recover some of the pressure that was lost. All right, so let's go ahead and take a look at another example. So here we have an equilibrium between hydrogen gas and iodine gas, which are the reactants, to hydrogen iodide, which is going to be products. And so going through the motions, how will the equilibrium shift when you increase the pressure or decrease the volume of this container? And so once again, we're going to go ahead and just count the number of particles on the left and right hand side of the arrow. So here we have 2 particles. And we also have 2 particles over here. And so this is a unique situation because the number of particles in the products and the reactant side are the same. And so whenever you get this type of scenario, there is overall no shift in equilibrium. Okay, and so the equilibrium will neither favor the reactant nor the product side, just because the number of particles is the same. Okay, and so the same is held true when you decrease the pressure or increase the volume. Once again, if the number of particles is the same, let me duplicate this. So 2 particles. When the number of particles is the same on both sides of the chemical equation, there is no shift in equilibrium. So neither the product or the reactant side is favored. All right, so let's go ahead and take a look at our final example. So here, in this case, we have a heterogeneous reaction where we have solid and gas state present in this chemical equation. And so once again, how will the equilibrium shift when you increase the pressure or decrease the volume of the container? So for heterogeneous reactions, in this case, there's a solid that's present. The equilibrium will favor the side that has the least number of particles that's affected by changes in pressure or volume. So there's kind of like an addition here. And so we're only considering the particles that are going to be affected by changes in pressure or volume. And so if you guys can think about the nature of solids, when you put a solid in a container, if you decrease the pressure of if you increase the pressure of the container or decrease the volume of the container, it doesn't really affect the substances that are solid in phase. And so here in this case, we're going to ignore solids because they're not affected by changes in pressure or volume. And so you guys have to just imagine that this is a chemical reaction in lab. And so in general, I mean, if you take a solid and you crush it, then that solid will be affected by pressure and its volume will also change. But that's not typically what we're doing in chemistry. So here we have, this specific substance and it's being converted into these substances. And so in the course of a chemical reaction, solids are not really affected by changes in pressure and volume just in general. And so what we really have here is 0 particles that's affected by changes in pressure or volume. And here we have only 2 particles that's affected by changes in pressure or volume. And so overall, according to what we wrote here, the equilibrium will favor the side with the least number of particles. And so in this specific scenario, for this example, the equilibrium will shift to the left. And by shifting the equilibrium to the left, we're able to alleviate the added pressure that we placed on the system. Okay, and so let's go ahead and take a look at the other example, in which here we have a decrease in pressure and increase in volume. And so the scenario really doesn't change between these two examples with respect to the number of particles. However, the equilibrium will change because here in this scenario, we're decreasing the pressure and we're increasing the volume. Okay. And so once again, the equilibrium will shift to the side that has a greater number of particles that's affected by changes in pressure or volume. And so for solids, we're going to completely ignore those particles. And so we effectively have 0 particles that's affected by changes in pressure or volume on the reactant side, and we have 2 particles that's affected by changes in volume and pressure. And so here in this specific scenario, the equilibrium will shift to the right. Okay. And so if the equilibrium shifts to the right, it's favoring the production of products. And since now you have more gas molecules in a volume of container that was increased, then the addition of those gas molecules will help compensate for the pressure that was lost when the volume of the container was increased. Okay, so that's pretty much it for this specific lecture video. I just wanted to quickly go through some examples on how to apply the theory behind changes in pressure or volume with respect to Le Chatelier's principle. All right, I'll see you guys in the next lecture video.